What's going on, everybody? It's Mr. Gust, and I'm back in the physics classroom. And today, we're going to be talking about one more kind of parallel between linear motion and angular motion. And so far we've discussed that outside torques are related to outside forces. Outside torques cause changes in linear motion, and outside torques cause changes in angular motion, and outside forces cause changes in linear motion. We then discussed kinematics and how angular and linear kinematics see parallels both in their motions and in their graphs. But we had to define what new angular motions were. But we have not really had a parallel to Newton's second law, which is the link between outside forces and accelerations, outside forces and kinematics. We know that outside pushes or pulls, forces, cause objects to change their motion, change their speed, change their direction. That's what outside forces can do, outside non-zero forces. And we know that both of those things are related to mass, right? The object's mass dictates how much an object accelerates or does not accelerate based on the net force acting on the object. And so we're assuming that there's a parallel between outside net torque and angular acceleration, but we don't know exactly what goes into changing that motion. And so today we're going to analyze a couple different demonstrations. I got a couple different tools we'll use here in the classroom and we'll look at to figure out what actually goes into this like mass component of rotation. Is it mass alone, or are there other factors that dictate how quickly or easily an object accelerates angularly? Before we do that, let's go ahead and reshape this idea around mass and inertia. So if I think about an object linearly, we know that an object with more mass has more inertia, and that makes it harder to accelerate. And an object with less inertia is going to be easier to accelerate. It's going to have less mass. That's what the definition, that's how we would use that term inertia. And today, we're going to analyze what rotational inertia is. Like, is it just mass? What dictates that? So I've got a few different demonstrations for you, and here's the first one. And if you're at home, you can obviously get some materials like this and try this at home, but the first demonstration I have for you is a broom. And all I'm going to have you do at home, if you have this at home, it's much better if you have these objects around the house. So if you do, go get them, pause the video, go get them, come back. If you don't, you can watch me do it. It's going to be less exciting. You're not going to feel what I feel, but I'll describe as best I can what I feel. So I've got a broom, and it's a short little broom, and I'm going to go ahead and grab this thing in two different points. I'm going to grab this thing down near where the bristles meet the handle and up here where the handle is, okay? If I grab this thing down here near the bristles and I give it a quick twist, it's pretty easy to use and rotate. I can even flick my wrist. Like at this thing, I've got all kinds of control over it. But if I switch it up and I grab it by the handle, now I can't do what I was doing before like I could with this. So it's clearly a difference in the ability to rotate this thing when I'm gripping it near the bristles. So there's obviously a difference in these two motions. And if I go ahead and find the center of mass of this broom, the center of mass of this broom is located more towards the bristles. Okay, the center of mass, this side has more mass to it than this side does. So, as I put my pivot point nearer that side, it makes this thing easier to rotate compared to where my mass is really far away. That's much harder to rotate. So when I think about inertia, clearly that object stays the same, but moving the pivot point changes the rotational inertia, it changes my ability to do it. So if I'm brainstorming rotational inertia, concepts, the same object can have a different rotational inertia based on its pivot. So the pivot point dictates the rotational inertia. And not just that, but in particular, its location relative to center of mass. Okay? The closer it is to the center of mass, it was easier for us. That was the first takeaway we had there. Different demonstration is my circus person demonstration, right? I've got this meter stick here. I have taped a mass to it, and I'm going to try to balance it. So if you have something at home, you could use that broom again, but brooms are weird. You could use a golf club. If you have a golf club at home, you can flip over side by side. But some object you could balance, a baseball bat, a softball bat, any kind of odd-shaped object that you might be able to balance on both sides. But I've just got a meter stick with a taped mass to it. You could do the same thing if you've got a meter stick at home or some kind of longer stick. Just wrap something heavy around it. Maybe you've got a weight at home. I don't know, a weighted ball. Who knows? Something to cause one side to be heavier than the other. If I think about this object's center of mass is obviously much closer to that mass. It's over here somewhere. So I'm going to try and balance this thing. And when I do, I try to balance it with the weight down. Go ahead and give that a try. I'm not very good at this, but if I go ahead and flip this thing over and try to balance it, well, this is much easier, right? I'm no Ava Wilson at this. Ava, in our first hour class, absolutely crushed the competition, balancing this thing, walking around the classroom. Good job, Ava. I'm no Ava at that. But clearly, there's something to balancing this thing with the mass up here as opposed to the mass down here. When I think about where my pivot point is at my hand. The mass is really close to that. When I flip it over, the mass is really far from that. So now I'm coming up with a new idea. As mass moves, so not just location relative, but as the mass is further from pivot, rotation is harder. I would say, in parentheses, more inertia. Okay, so that's another takeaway, right? As the mass not only is further from the pivot, now there's more inertia there. So it's definitely related to mass. And again, I didn't change this object's mass when I flipped it. I just changed its pivot point and therefore the location of the mass relative to that pivot. Let's go ahead and try a new problem, or a new demonstration. I'm going to come all the way over here. And when I come all the way over here, I'm going to have you with me, and I want you to watch something. I'm going to move these boards out of the way. I'm going to get a second meter stick. I'm going to have you predict which object will hit the ground first. I've got two of these sticks now. I've got two of my balanced sticks, and I'm going to place them against the wall. If you see over here, I've got my wall right here. You see the ground? We can almost see the ground. Let's go a little more. There we go. Now, if I drop these in the exact same location, from the same height, I drop them at the same time, they're going to hit the ground at the same time. But that's not what I'm going to do. I'm going to go ahead and move this one around this way, okay? So I'll move these objects like this. One mass is located at the base of the wall. One mass is located towards the edge. I want you to pause the video now and predict which of these objects is going to hit the ground first. They clearly have the same mass. They're made of the same shapes and the same objects, but relative to the pivot point, the mass is distributed differently. So go ahead, pause the video, make a prediction. I will wait. Did you make a prediction? I feel like Dora the Explorer right now. Like, what's your prediction? Did you make a prediction? Let's find out. We're going to drop them to the same height in 3, 2, 1, go. And it looks like the object, this one drops first, the one with the mass. I'll go higher to like maybe exacerbate what I'm seeing here. 3, 2, 1, go. Definitely. This object right here drops first, and this object here drops second. That shouldn't surprise you. Which object was further, or which object had mass further from the pivot? It was the object that hit the ground second. It's harder to rotate. It's harder to rotate. It has more inertia, therefore it hits the ground second. It starts slower. Okay, fine. One more demonstration, one more, because those are all pretty weird, unique, like weird situations. We don't see a lot of balancing acts like that. What we do see are objects like this. we do see discs and hoops and balls, and this is what we see. And so because we see these things, let's examine how they roll down ramps, because we should be able to apply this concept of rotational inertia to rolling objects. So here we go. I'm going to go ahead and do my best. I'm going to have only 2 hands to get 3 objects down this ramp. You can see my ramp right here. I'm going to release all 3 objects, hopefully at the same time, and hopefully they will all roll together. All right, let's just see what happens. Let's see which of these objects makes it down the ramp fastest. It's a pretty steep ramp, I guess. Oh, it's not too steep. Ready? 3, 2, 1, go. The hoop is last. The disc and ball are pretty darn close, I think. So if we rank these in terms of their ability to speed up from rest, we would say this guy's the loser. We would say these 2 are pretty close. Maybe we should try them both again just to figure out and see if we can get a better viewpoint. Ready? 3, 2, 1, go. It's a close race. It's a close race, but I think the ball wins. I think the ball goes down faster than the disc. If I had to do it, you can go back in slow-mo if you want to, if you're really that concerned about it, but, take it from me, it's the ball. The ball's faster. And so what does that mean? If we go back to, we've kind of brainstormed so far, as the mass gets further from the pivot, rotation is harder, therefore there's more inertia. The hoop has all of its mass located at the edge. All of its mass is located far away from the pivot because the pivot is this arbitrary point in space. Comparing the disc to the ball, if I look at this, the ball has got mass distributed everywhere. Here's its pivot. It rotates around here. There's mass evenly distributed everywhere on this object compared to the disc, where the disc has like a cylindrical side to it, right? It's got a flat side, so there's no mass located at the edges. This mass is located further on average from the pivot or the axis of rotation than the sphere. Not much. That's why their race is really close, but not much. But still, nonetheless, there is a difference in their rotational inertias. Okay, if I think about the things that dictate rotational inertia, we obviously know mass has to play a part, and we obviously know radius. And what I mean by radius is the distance from pivot, right? Distance, the radius of the object, the distance from the pivot. This matters. And then m is the mass of the object. These 2 factors play a role in an object's ability to begin rotating. So it's not just mass, it's rotational inertia. It's everything tied together. Sometimes it's called moment of inertia, but its variable is I. And we have a lot of various I values, right? Every object has its own I equation. For example, I of a hoop is equal to mr squared. I of a disk is equal to 1/2 mr squared. Notice the hoop has a much larger, almost double rotational inertia or moment of inertia compared to the disk. The disk is half, which kind of makes sense if you think about where the mass is located. And then lastly, we have got our sphere or our ball, which has an I value of even less than the disk. I of the ball is 2/5 mr squared. So we're seeing a pattern. As that coefficient decreases from 1 to 1/2 to 2/5, our rotational inertia decreases. The objects speed up and slow down much easier, like the ball to the disc to the sphere. This is our second law of rotation. Torque net equals I alpha. It's our direct comparison to F equals ma. What is I? I is rotational inertia. What does rotational inertia depend on? It depends on the mass of the object. It depends on the location of the mass in that object relative to the pivot point. Prime examples are our broom, our meter stick, our disc, sphere, and ball. These are prime examples of how objects that have the same mass but different locations of pivots can cause different rotational inertias, can cause different accelerations angularly based simply on where their pivot point is. We will go into more math around this later, but for now, I want to make sure you all have a firm understanding of the background on what is I, what goes into I, and how this equation relates to our second law of linear kinematics, or linear motion, F net equals ma. Well, now we've got torque net equals I alpha. If you got questions, drop in the comments, send me an email, or ask me in class. Until next time, see ya!